Actually, it's our last topic, introduction to hashing. Yeah. After this topic, we will complete this topic this week. Next week, we will start review for the final. Because next week, that will be our last week of this semester, regular semester. Then our final week. So the last week, we will do review. All right. And before I start my presentation today, I like to talk about, a few important things, because some students ask me about that. So let me answer here to everyone in the class. The first thing, grading thing. First thing, grading. First, I do grading midterm because I haven't started midterm grading. Due to, I have a big paper to submit. Yesterday, I just submitted that paper. So now I will, speed up the grading. After the class, I start midterm grading. So most of you will see the grading result of midterm sometime today or early time tomorrow. After that, I do grading, project one. So I'll try to, give you the result in a few days. Because some students are, waiting for these two grades to see if they can get a good grade at the end of the semester. So that's one thing. But another thing is, a few students also ask me for extra credit chances because they feel they do not get their grades good enough, so they want to improve a little bit. So here I think about, some extra credit chances. First, we need to notice that we do not have much time the remaining of the semester, so we cannot do a lot of things. Okay, so I try to control, reasonable amount of work. Do not give you too much work. All right. So here, because we have 4 quizzes at this point. Based on our plan, we have another quiz, but also another homework assignment I want to combine. Because 2 assignments, that's too much for you, right? So I merge the last 2 assignments, quiz 5 and homework number 2 as one assignment. The first thing, before this extra credit. I talk about the extra credit after this one. First, we merge these 2. One is quiz 5, another is homework 2. How to merge? All right, the merge way in the quiz style. The quiz style, the quiz style. So currently the quiz, the questions I will give you like our quiz questions, not our homework style. Homework, you need to write on PDF, right? Upload. Quiz style, you just do it on the Canvas tool directly. So that's why I say quiz style. And 15 questions. our usual quiz questions, 10 questions. Yeah, but our homework question, 25 questions. So when we do the merge, I just make 15 questions. Okay, yeah. In this one, after the merge, so this assignment, we can count it both. Yeah. One for quiz 5, another for homework 2. Yeah. So the grade, we count it, for those 2 assignments in our calculation. Okay. Yeah. Hope you try your best to complete it. But the quiz one, we drop the lowest too. Okay. So we still have that policy, drop 2 lower scores. Okay. Yeah. So that's for the reduction part. Yeah. I do not want you to do too much work. And this one, you will have it this weekend. Yeah. Because you need about still a little more than 1 week to complete it. Yeah. So this weekend, before the end of quiz 4, I need to assign this one. Yeah. All right. So that is this one. Then extra credit. Yeah. Extra credit. Yeah. 1. One written assignment. Yeah. So just, like the PDF one, but this is the optional one. Yeah. This is optional. Optional. Okay. Yeah. Optional for those students who do not have a lot of time, so you do not have to do. All right. Only those students who like to improve their grades, so you can try this chance. Okay. So this is optional. So written assignment with 10 questions. Yeah. I do not give you too many. Yeah. Too many, then too much work. Oh, let me view that chat message. Yes. All right. Does that mean we'll have total of 5 quizzes? Right. Correct. Right. 2 low job. Yeah. Correct. Quiz grade depend on 3 highest. Yeah. 3 highest. But remember, in our syllabus, we need 4, right? I will scale the 3 highest to 4. Yeah. Just multiply 4/3. Yeah. Scaled up to get a, 4 equivalent quiz numbers. Yeah. All right. So don't worry. Yeah. So we won't lose any. Yeah. Yeah. In this way, hopefully, you can get a better grades. All right. Regarding this optional, so 10 questions. These 10 questions basically computation questions. Those 15, we know, concept questions. Concept questions. Okay. Yeah. Concept question. And these 10 computation questions. Yeah. All right. Yeah. So you can see the original 25 question we split, right? We split 2 parts. The first part, 15 questions. So we use as the, regular assignment. But the last 10 computation questions, relatively harder. So I make it optional. Yeah. So for some of the students, they have workload reduction, right? If they are too busy. Yeah, some students in this final period of time too busy. Yeah, so you have option. So if you feel so you can handle, so you do not have to do these 10 questions. Yeah, but these questions, although you do not do it, you do not spend time work on it, but when I do review study, you need to study the solutions. Okay, so when I explain the solutions, you need to try your best to understand. Yeah, because in the final, we will have similar questions. Yeah, for those who like this extra chance, so yeah, so they can earn. Yeah, how much extra credit? I will give you. Yeah, 3% overall extra credit. That's a lot. Okay. Yeah. So if you work on it, spend time, you're willing to spend time, yeah, it's worth it. Yeah. Although it's a little harder, yeah, it's worth it. Yeah. So that's the first chance. Second chance, also optional. Yeah. So not required. Yeah. Extra credit optional. Project 2. So it's optional. Yeah. So remember in our midterm, I mentioned that Vigil of log base 2 Fibonacci numbers, algorithm to find Fibonacci numbers. In our textbook. Yeah. The detail in our textbook. Yeah. But I will give you the details. Okay. I will give you the implementation details. Okay. Yeah. Prepare you, explain how to do the computation. Yeah. But you need to write a code to find the answer. Yeah. Still, you need to do some work. Yeah, because this is an optional extra credit chance. You do not have to do. Yeah. But if you are willing to do it, you have good chance another 3% overall extra credit. Also, pretty significant. Okay. Yeah. Because that's the reward for your extra effort. Okay. Yeah. All right. So these two chances, yeah, at least for those students who, because they set their goal pretty high, so give them chance to reach that high standard they set. Okay. Yeah. But it's not free, so you have to do this much work, to understand the material better. Yeah. All right. And in the limited amount of time, yeah, very limited, very tough. So that's why it's not easy. Yeah. But for the other students, I try my best to reduce the workload. Okay. Yeah. Yeah. Try to make not overwhelming for you. Okay. Yeah. Try to make it reasonable. Yeah. All right. So that's the plan. Yeah. And yeah, try to, based on your needs, so you can choose how much you want to do. Okay. Yeah. All right. So then let me, if you do not have any question, let me go back to our previous lecture notes and we complete the remaining part. Yeah, but because I still have some quite important topic left. Yeah. Let me get out here. I will come back later to this new topic. Old topic, that's this one last time. Yeah. And we are, yeah. So last time we just complete this part. Yeah, remember last time at the end, we need to do summation, this S summation. Yeah. Yeah. Let me just start right here. Yeah. All right. Yeah. Yeah. Get to the point we left last time. Yeah. Right here. And yeah. Yeah. All right. So last time we need to find the summation of this one. Yeah. It is a little harder. There is some smart trick here we need to apply. Otherwise, it's not easy to find the answer. So first, let me show you that little trick here. Yeah. Calculate this summation, this S. Yeah. The numerator, you can see the pattern, 1, 2, 3, 4, the consecutive numbers. This H, we know the height of the nodes we work on in the heap. Yeah. H height. Yeah. The denominator power of 2. Yeah. So here you can see the numerator and denominator, they have two different patterns. And when we do the operation, we need to take advantage of these two different patterns. All right. So the trick is very simple. Yeah. First, we work on the denominator part. Yeah. Think about its power of 2. And when we multiply 2, both sides on that equality, you will see 2s left-hand side equals the right-hand side. You multiply by 2, there you only need to reduce the exponent number in the denominator by 1. Yeah. But after that reduction, you will see you basically shift the terms, shift the position of the terms when you compare with the original S terms. Yeah. Now look at the corresponding terms. That means the denominator 2 squared. Let's look at the terms with denominator 2 squared on these two lines. Then the numerator, the first one numerator 1, the second one numerator 2. Look at this pattern, this relationship. Okay. Then another one, the corresponding terms, same denominator 2 cubed, but the numerator 2 and 3, the lower one is 1 more than the upper one. Look at that relationship. The same as the previous red circle, right? Yeah. Then we keep checking. You will see we have this pattern all the way to the infinity. Okay? So we can take advantage of this pattern, this rule. How to take advantage of this special rule? Subtraction. subtraction. We use the lower summation to subtract the upper one. So we will get S, left-hand side just S, 2S minus S, just S. Then the right-hand side, very simple. Yeah. Denominator power of 2, the numerator all ones. 1 over power of 2. We know this is geometric series, right? And we have the formula, calculate the geometric series. Now here, let me just remind you the formula. Yeah. 1, yeah, actually, the first term, yeah. Yeah. So let me recall the formula, okay? Yeah. S equals A times AR times AR squared, common ratio, right? The formula gives us A over 1 minus R, okay? A over 1 minus R. Here, our A, this is our A, 1/2. 1/2. 1 over R. R is also 1/2, right? Yeah. So 1/2 over 1 minus 1/2, also 1/2. That's 1. The answer is 1. Yeah. All right. S equals 1. Yeah. All right. And that's our S. Look at that's our S. Because we need to find S. So that's our S. So we get a result. Now we can go back to our building heap cost estimate. In our building heap, remember we have 2 summations. One summation last time we did it. It's pretty simple. And now this one. This one, remember, we can take that n out, right? The remaining thing, after we take n out, the remaining thing, big O of 1. Look at this one. Big remaining is that S. So the remaining thing becomes big O of 1. Then that n, after we bring out, we can bring in and multiply that. So we get a big O of n. So the summation, the first summation, we get a big O of n. What's the second summation? We need to bring it back here. The second summation, we bring it back. Log of n squared. Comparing with n, this log of n squared, too small. So we can ignore it. Yeah. Too small, right? Yeah. So we just ignore it. Then the final asymptotic notation is this big O of n. That means building a heap, the cost is big O of n. That's the final cost. Okay? Yeah. In order to do the heap sort, we need to build a max heap first. When we build it, we need to pay certain amount of cost. How much is that cost? Big O of n. That's the cost. Not too bad. We can take it. Okay? We just take it. Big O of n. All right? Then, next step, we need to do the quick sort. After we have that max heap structure, now we are ready to do the heap sort. So the last subtopic of this lecture, heap sort, the final step. All right, that's pretty easy. So let's do the heap sort, including the efficiency analysis. Yeah. That part also very simple. Yeah. So we put together, we complete this topic. Yeah. Let me show you, let me use the diagram to show you the procedure. Yeah. So simple and very smart. Yeah, very smart. Uh, this is the heap structure you see. Yeah. Near complete binary tree. Only the bottom level may not be full. Other than that, all the remaining levels are full. All right. And when we start, after we apply that max heapify, build a heap, actually, build a heap, we need to do that max heapify operations many times, bottom up. At the end, we get that max heap. Okay, yeah. So here you can imagine we have that max heap. Before we do the heap sort, we have this max heap first. All right. Then, based on the max heap property, the largest element is at the top, at the root. The max element at the root. Okay, yeah. There, because we know this element is the maximum of the whole array, we can put it in place quickly. Put it in place. Its place is at the last element, right? The maximum should be at the end of the array. That's the last element. All right? Yeah. How do we put it in place? Do one swap operation. Swap the root with the last element in this heap. One swap operation. The max root, that's the first element in the heap. Its current location is the first element in the heap. Final location, the end element in the heap. We just do one swap operation. We can get it. That's simple. All right? Yeah. Swap A of 1 and A of n. We put a one element in place. Okay? But the swap would cause the max heap property violation, right? Yeah. You put the last element on top, there is violation. But we can fix it, right? We apply the max heapify operation to fix that violation. Yeah. Recover the heap structure by that max heapify operation. Because it is just on one node. So we apply it. We use iteration way. Because we will do this again and again. Okay. First, we build a max heap. Yeah. So that's the big O of this step. We need to pay this much cost, big O of n. After that, we do a for loop. Every time we put one element in place until we put all the elements in place. Okay. For I equals n down to 2. Yeah. Because when we put the element corresponding, the second to last element in place, then we put all elements in place. So that's why down to 2, not down to 1. Yeah. Because the last one are automatically in place. So we do not need to do anything for the last one. Okay. So down to 2. Yeah. All right. Swap A of 1 and A of I. At the beginning, I equals n. So we swap A of 1 and A of n. After that, A of 1 and A of n minus 1, and so on. Okay. After that swap, we need to fix. We need to, first, before we fix, we reduce the heap size by 1. Yeah. Because the last element already in place, we should not consider that element already in place. So that's why we reduce the heap size by 1. Okay. After that, we run that max heapify operation to fix the max heap property violation at the root. This 1 means the root position, right? We always fix it at the root position, all the way down to the bottom. Yeah. So recall our max heapify operation last time. Yeah. All right. So this iteration again and again, and down to 2, we get all elements in place. All elements in place. Then the array is sorted. And that's simple. Yeah. Yeah. So this is the whole procedure of the heap sort. Okay. Yeah. Whole procedure in the heap sort. Yeah. Let us just estimate the cost. The cost estimation is also pretty simple. Yeah. Think about that. Let's look at the max heapify operation cost in each iteration. The first iteration, because the array size, the heap size is n, so that cost is log base 2 of n. Okay, yeah, from top to bottom going down. Yeah, so we know, yeah, last time from top to bottom, number of levels, log base 2 of n. That's this one. Okay, the next one, log base 2 of n minus 1, and so on. Every time the heap size is reduced by 1. And the last one, the heap size is 2. Yeah, so we do another log base 2 of 2, that cost. Now we just estimate the summation of this one. It looks not easy, but there is an easy way to estimate. Yeah. Because each term less than or equal to log base 2 of n, right? Yeah. Only the first one equals log base, the remaining all less than log base 2 of n. Yeah. And we just use this log base 2, so we will get this whole thing less than or equal to, there are n minus 1 terms, right? Each one we use the larger one, log base 2 of n. This minus 1 can be ignored, right? Too small. Yeah, so less than n times log base 2 of n. Yeah, this estimate. That means this one we can write big O of log n log n. How about that? N log n. Okay, yep. That's the final result. Our heap sort, we can get n log n efficiency. N log n. Yeah, this simple estimate. Yeah. And this estimate is pretty rough. Here you can see I use this inequality. It's pretty rough. Not very accurate, pretty rough. But there is an accurate way. More accurate way, we use integral, definite integral. We can do a very accurate estimate. But good thing is the answer is the same thing. The answer just differs by some constant. Constant different. Constant times this number. Yeah. Lower bound. Lower bound, the major part, the growth function still n log n, but only the constant, leading constant is different. Leading coefficient is a different constant. Yeah, that's fine because we know the constant is not important here. Yeah. So the answer is still this n log n. Yeah. So here I do not go to that definite integral. We need to do a lot of calculation. Yeah. Yeah. All right. So after this, so the heap sort satisfies all the requirements we need. we discussed at the beginning of this topic. Yeah, so that's a interesting solution. Yeah, but if we go back to our discussion before, if you need the best overall sorting algorithm, the best overall, quicksort is the choice. Yeah. So that's why if you do not have any special requirement, then people pick the quicksort. Only when you have some special requirement, then you need to consider other options. Yeah. The quicksort, we know it has the problem. Its worst case is n squared. Yeah. So let's just go back to the quicksort a little bit. Yeah. Yeah. Its biggest problem, its worst case in this big O of n squared, not n log n. Yeah. That's something we like to avoid it sometimes. Yeah. Yeah. If we apply sorting algorithm large number of times, and this worst case just occurs in very small percentage, let's say 0.001% chance, then we do not worry about it, right? Yes. Yeah. So then, because we emphasize overall performance, the overall performance, this quicksort is the best. So we still would take it. Yeah. All right. Yeah. All right. So that's the discussion of the divide and conquer the our module 4 topic. Yeah. The biggest module. So you can see we spent more than 1 month. Yeah. Although we spent a lot of time review for the midterm, right? Yeah. A lot of sessions we spent on review sessions for the midterm. Yeah. But the overall, we spent more than 1 month on this module 4. Yeah. All right. So then let me switch to module 5. Yeah. So the previous PowerPoint, yeah, this one. Now, let me move to the new topic, hashing topic. Yeah, it's an interesting one. Yeah, because hashing very useful. Yeah, so I like to give you the general method description. Yeah, and the lower level details, I skip. Yeah, to save some time. Yeah. So the higher level understanding, yeah, hopefully good enough for you. Yeah. Because in the real world, you may have a lot of chances to apply this hashing technique. So you need to have plenty of background, understand this hashing technique. Okay, all right. Here, let me describe the question. This general title, how to find a data item with a given key. Yeah, this is a search problem, right? And currently, we already have the linear search and a binary search. And then this one, hashing, the third searching algorithm. So we need to compare it with the linear search and the binary search. All right. Given a collection of data dynamically, here, this is the situation we are facing when we solve this problem. Yeah. We have a collection of data. How much amount, we do not know. Okay, yeah. On the fly, the data comes in on the fly, so dynamically. comes in and go. Yeah. Sometimes we need to delete some data items. Sometimes we need to add data items. Dynamic way. Yeah. All right. Yeah. And then for each data item, there is a unique key we can use to identify those items. Okay, data items. Yeah. Keys, key-based search. We need some key, good key to use. Yeah. All right. The key unique. Yeah. That's no problem. Yeah. All right. The question, how to make your data search efficiently? We want to find the fastest way. Yeah. You can choose how to organize your data, how to arrange your data. You have the freedom to do that. But after you arrange your data in some organized way, we want to enjoy the result of your data organization. That is, the searching performance is very fast, extremely fast. That's our goal. Okay? Yeah. How to make that happen? Yeah. The idea actually pretty simple. Yeah. Here, first, let me talk about the idea. Okay. Data structure is not a given. Yeah. So nobody tells you what kind of data structure should be used. Yeah. That means you have freedom to choose some special data structure. Yeah. Yeah. So we need to take advantage of that freedom. Okay. Yeah. Because in order to get extremely fast search, our data structure should be very special with special properties so we can use. Okay. Yeah. Handle dynamic data efficiently. Yes, you need to consider deletion, insertion. Those operations also very fast. Deletion, insertion, also very fast. Okay. Then you have a good algorithm. Yeah. With all these factors considered, then you can have a good searching algorithm. Okay. Yeah. So this is the background description. Yeah. And before we look at the algorithm detail, let's do some comparison. Our known search algorithms do some comparison, yeah, including linear search, binary search. But there is another search, not well known, yeah, not well known, but very extremely simple. So I also put in this chart for the comparison. Yeah. The first one, first column, linear search. Second, binary search. And there is one little one, very small, not frequently used. Yeah. That's called index search. Very simple index search. Yeah. I will explain. Yeah. Then let's do comparisons. The data structure used for the linear search, array, binary search, also array, index search, also array. Yeah. Actually, from this name, you can see the index search pretty straightforward. That is, we have data stored in array. We just use indexes as the keys to do the search. You can imagine how fast it is. Given index, we can find the element immediately, right? We just go to that index location. We can retrieve the data item we need. So that one we call index search, all right? Yeah, simple, fast, but why it is not popular, not very useful. This search is not very useful because it has a big problem. too big. This problem is too big, and nobody wants to use it. Yeah, I will talk about that later. Okay, yeah, huge problem in this index search. But the reason I put it here, because there is some interesting property in this index search. We can use it. We can borrow for our new algorithm. So I put it here. Yeah. All right. Performance or efficiency, you can say. Yeah. Linear search, bigger of one. Yeah. We're familiar with this one. Binary search, bigger of log base 2 of n. Yeah. Much better than a linear search, but data should be ordered, right? Linear search, we do not require the data ordered. So big O, yeah, so we can have this big difference. Yeah. The index search, much faster, big O of one. Yeah, because you can retrieve the data immediately. So that's big O of one. The best you can get, right? Yeah. But its problem is extremely big. Yeah. So we will get there. All right. Next, ordering. Yeah. So order when, how do you organize your data? In an ordered way or unordered way? Linear search, no such requirement. Unsorted, unordered, okay? Sorted or ordered, yeah. Unsorted, yeah. Index search. Order is not considered in the index search. Okay, all right. Dynamic or not? Yes. If your data comes in and goes dynamically, to maintain dynamic data, how much is the cost? Yeah. So you can do dynamic way, but the cost could be high. Yeah. Yeah. Oh, the linear search, the cost. Yeah. So when you add a dynamic data, you add at the end of the array, right? Yeah. So that may not be high. Yeah. But for the binary search, when you add data, you need to put it in place, right? That cost is, pretty high. Put it in order, right? Yeah. So that operation is costly. Yeah. And index search, you just put it at the end. So that operation is very cheap. Yeah. Efficient sorting. Yeah, because sometimes you want to get your data, in order. Yeah. So you need to consider that factor probably. Yeah. Not efficient. No. Yeah. Linear search, it does not have this property, efficient sorting property. No. Okay. Yeah. When you need to do sorting, it is very expensive. This one, very efficient. Yeah, because you already make your elements ordered. Yeah. So the sorting already there. Yeah. Also expensive. Index search, you need to do the sorting. So very expensive. Okay. All right. So that's the known algorithms we have at this point. Yeah. For our new algorithm, we need to borrow some of the ideas from these known algorithms. So our new data structure, we need to have some new data structure. Yeah. If it's array, not good enough. We need more properties than array. Okay, yeah. Then the performance efficiency, we want close to index search, bigger of one. Extremely fast. Okay, yeah. But later you will see it will not be as fast as index search. Yeah. It has best case, worst case. Its best case is very fast, big O of 1. Its worst case, not very fast, big O of n. It's worst case. Pretty bad, its worst case. But its average case is very good. Average case also big O of 1. That's good enough. Okay? So the average case is big O of 1. Yeah. Ordering property unsorted. Yeah. So we cannot have that. If sorted, then that's the binary search case. So we cannot do this fast, big O of 1, this fast. Yeah. So it must be unsorted. Yeah. Dynamic supporting that, yes. Yeah. So we can add new element into our data structure in a very fast way. Yeah. This property, we will have it. Okay. Efficient sorting, no. Yeah, because if you want to get your data sorted, it's still very expensive. You cannot get everything, all the properties you like. Yeah. You have to sacrifice some of the properties. Yeah. This last one, yeah, that's the biggest sacrifice for this new algorithm. No efficient sorting, the biggest sacrifice in this searching algorithm. Yeah. Okay. All right. Yeah. So here you can see very similar to that index search. Yes. Actually, we borrowed the idea from the index search. But index search has a huge problem. After we fix that huge problem, then it becomes our new sorting algorithm, the hashing one. Yeah. The name is the hashing technique. Yeah. But we need to fix that huge big problem in the index search. Yeah. So first we need to know what's that big problem in the index search. Okay. Yeah. All right. Yeah. So next, yeah. Today we do not have much time, so let me try how much I can go. Okay. I have 10 more minutes. Yeah. Try to explain, yeah, this index search idea, generalize the idea of index search. Yeah. So in our textbook or in other algorithm books, it's called direct addressing. Yeah. Because the index, that's the location, the key index. We use indexes as the key, search keys. So the search keys directly give us the addresses of the data items. So that's why its official name is called direct addressing. Okay, that's the main property of this search algorithm, direct addressing. Yeah. Yeah. All right. Its key property, yeah. Key index of the array, that's the location of the element, the same. Yeah. The same thing. Okay. Yeah. The main problem. Yeah. Let's look at its main problem. Yeah. When the keys are long, yeah, think about it. Sometimes the search keys could be long, then you will have some big problem. Yeah. But you only have a small number of elements. Think about this special situation. Yeah. Long keys with relatively small number of elements. You waste a lot of space. If you still use those keys as the indices of the array, you would waste too much memory space. That's the biggest problem. Okay? Yeah. Here we need to answer this question: how to use space efficiently. Yeah. because your sacrifice is too big. In order to get a faster search, you waste too much space. That's not acceptable. Okay? Yeah. So that's why. So nobody use that index search or direct addressing search algorithms. Nobody use that. Yeah. All right. Long keys. Here, I like to give you a simple example. So you will see this method is not acceptable in the real world applications. Yeah. Think about a common way we use as the search keys. One is social security number, another is the student numbers. Usually, those keys have many digits, right? Long digits, yeah, 9 digits, 8, 9, relatively long digits. Yeah. Think about in a typical class, if we have just 40 students, that's a small number, right? But if you want to use the natural search keys, social security number or student numbers, just for 40 students, but you use those keys as indexes directly, you need to create a huge array. You will waste too much space, right? It's a huge waste. Yeah, that's not acceptable. Okay, so that's not acceptable. So in order to make this search algorithm useful, we have to fix this problem. Space waste problem. Only after we fix it, then it is useful. But after you fix it, then that's the new search technique, hashing technique. We do hashing. Yeah. When we do hashing, we do not need to use that much space. We can greatly reduce the number of wasted space. Yeah. Okay. Yeah. So let's look at the details. Yeah. How to make keys shorter. Yeah. The problem is those keys are too long. That's why the space usage is not efficient. How to fix it? Can we make those keys shorter? Right? If we can make it shorter, then we compress the wasted space greatly. So that idea is so simple, right? Pretty straightforward. But the questions, when you make those keys shorter, you need to you need to fix a lot of details. Yeah. Yeah. The idea is simple, but details is not that trivial. You need to pay attention to a lot of details. Yeah. All right. How to map keys to slots. Yeah. So the question becomes mapping keys to the slot locations. It becomes a mapping problem. If you can find a good mapping way, then you would get an efficient search algorithm. That's simple. Okay, that's simple. Yeah. So the final problem to be solved, solving this efficient mapping problem. Okay. Yeah. Mapping strategy. Yeah. So our remaining discussion all about mapping strategies. Okay. Yeah. The mapping should be easy and efficient, you know, but we may have a lot of small sub-problems to be fixed when we design those mapping strategies. Yeah. All right. What is a good mapping? Yeah. Yeah. All right. First, fast calculation. Yeah. Mapping, we know we need to do calculation, right? Yeah. Given a key, how to find its mapping location. Location. Yeah. So here we imagine the key as an input parameter. It's an input. Input is the given key, search key. And suppose we have a function. Yeah. We plug in the given key as the input into certain mapping function. Yeah, mapping and a function, similar, right? Yeah, mapping and a function. Yeah, similar concepts. Yeah. So we plug in into certain, yeah, at this point, unknown function. Yeah. And we do calculation to find the function value, right? And we expect to have fast calculation. Yeah. Otherwise, if it takes a long time to do the calculation, then your search algorithm cannot be very fast. You need to wait a long time to find the key value or find the function value. That's a better mapping strategy, right? So the first property, fast calculation. Second property, evenly distributed among all the slots. Yeah. So at the end, you need to distribute those data items in the certain number of slots, right? If you distribute in a narrow range, then the performance won't be good. Okay, so when you distribute the locations, mapping locations for your data items, it should be you want to have evenly distributed behavior for the mapping. Okay, yeah, that's the second property. Yeah. Third one, not sensitive to any pattern. Yes, this is also important. Yeah, because when we are given a sequence of keys, sometimes those keys may satisfy certain pattern, certain special pattern. Okay, but if your mapping strategy or functions, hash functions, cannot, do not perform well for certain special pattern. So when you hit some special pattern, it becomes very bad. Okay, very bad here, it means the mapping locations focus on small area, small region in your clusters, not widespread, not evenly distributed. Yeah. That won't be good. Yeah. So you want to avoid that. So not sensitive to any pattern. Yeah. So these three properties most important in our mapping strategy design. Yeah. All right. Yeah. So let me stop right here. Yeah. Here I just talk about the general idea. Yeah. Next time we will look at the mapping details. Yeah. Because that's the most important part. I will talk about commonly used the mapping strategies. After that, we complete this topic. Yeah. So we just go that far. Okay. The mapping strategies. Oh, after that, there is still, we fix the resulting problem. Yeah. After the mapping, we have another problem we need to fix. So after that, we complete this topic. Yeah. So in this week, our final lecture, we will complete this topic. Okay. All right. So let me stop right here. Yeah. And I will post this video as soon as possible. And also, I will go to the grading of the midterm quickly. Yeah. All right. So